All right, now I'm going to talk about an interesting idea in a conversation I had with Susan about her thesis. So she's interested in something called stress strain curves. And stress strain curves have this property where you're plotting stress, where maybe you push two things together, or strain, where you pull things apart. So strain is, we can think of strain as pull, and stress is push, generally speaking. Okay, so that's where we have a stress strain curve. It's common in mechanics, and she's looking at tissues, especially tensegrity objects that experience this kind of curve. And usually, you'll have a curve. It could be like this. It could be like this. It just describes the relationship between stress and strain. Now that's interesting, but we can do something else with this. We can use this as a phase space, so we can have a stress strain phase space, or a push-pull phase space. So we get rid of the stress and strain terms. In general, we have push and pull. So let's divide this into quadrants. Let's define these quadrants. So the upper quadrant is low push, high pull. And then the lower one is low push, low pull. So you see what we're doing? We're kind of taking these possibilities and we're recombining them. Now, when you have low push and you have low pull, that's basically where something is static. So if we have like this stack of cells here, this is where we don't really do anything. We just leave it alone. It's not being pushed. It's not being pulled. There is no compression. There's no tension. There's no stress. There's no strain. And so this is our static condition. Up at the top, of course, if we have low push and high pull, we're not introducing very much push, but we're pulling this stack out or apart. And so that's pull, and that is some sort of tension. Because the whole stack is in tension, introduced by this pulling. So this is tension. Then at the lower right, we have low strain. And we're following the conventions of the axis. And high stress. All right. So in this case, this is what we call being in compression. And what that looks like in terms of our stack, we're introducing some minimal strain forces, but we're introducing a lot of stress forces. So we're pushing our stack inward. And we're pushing it together, pushing all the cells together. So again, in low push, low pull, we don't do anything to this stack of cells. In a low push, high pull environment or a tension environment, we're pulling them apart without really providing any sort of push forces. Maybe they're local or minimized. And then in the compression, we have pull forces which dominate, and that is compression. This is where we push things together and pull things out in a limited fashion. So we end up with these two modes, tension and compression. And then the top one here is high pull and high push. And that characterizes dynamic behavior. So in this case, it's almost like an accordion. We have our stack of cells, this. We're introducing pull forces. We're introducing push forces. And they're more or less equivalent, but it basically moves in and out like an accordion, so they're dynamic. So we have this region here in the middle where you can either go in this direction or this direction from dynamic to static. So you can have the accordion model, which you see here, or you can have this static model, which we see here. I'll just put the static model up here just so that we have it. So we have these forces that make it go like an accordion, in and out, in and out, or we have the static case where there's nothing there are no inputs at all. We can move between those two quite well. You can imagine a situation where you introduce forces and then you stop introducing forces, or you start introducing forces from a 0 point and you move it from static to dynamic. Or you have dynamic to static when you stop playing these cells like an accordion and they go to the static resting state. So this is kind of a resting state. And so then these other modes, tension and compression, are sort of the side conditions. So you can move from static to tension, tension to dynamic, or dynamic to compression, compression to static. And so you can see that how that works. What's interesting about the accordion model, though, is that you can hook this up to an oscillator. So if we have like an oscillator, like a sine wave, we can actually hook this into the accordion. And we can play this in sort of this rhythmic way where we have tension and compression, tension and compression. We can also modify the sine wave so that it's aperiodic. So we can have a sine wave and an aperiodic wave. And they can have different effects on this system where there's this dynamic system. And it's providing dynamics to this set of cells. So it's interesting that, depending on the structure, if it's maybe a tensegrity structure or regular structure, it responds to these different modes in different ways. And we have this driving force, this sine wave or this aperiodic wave, or any other standing wave that you want to put into the input as the input, and you can get different types of behaviors. Now, one more thing here is that just because you have one stack of cells doesn't mean that you're done, because you can have multiple layers of cells like this, and you can have multiple sources of input. So you can have things under compression like this, or things under compression like this. Things undergo tension in both dimensions. Actually, in multiple dimensions, you can have a third dimension where things are being compressed and put under tension. And so you have all these different routes to sort of inputs to this layer. And you have multiple layers of cells. So each of these layers respond differently depending on the material properties, and each of these layers sort of respond. Maybe the forces and inputs are anisotropic. So that's another property that we have here, is anisotropy.